And with that, good morning everybody. Welcome back to Calc 2. Hope you all are enjoying yourself on this lovely, lovely day. Enjoying Winter Storm Otto, I believe. Plan for today is we're going to continue our discussion of improper integrals. Probably getting most of the way through the rest of the packet. Not quite sure if we're going to finish the packet today, but if we don't finish today, we will finish off beginning of class on Friday. As far as office hours goes, I have to make a slight change to my office hours today. I've got a contractor working on my house right now, and I have to meet with him this afternoon. Unfortunately, I couldn't reschedule it, so I have to cancel my afternoon office hour today. I'll still be around today from 11 to 12, and to make up for my missing an office hour this afternoon, I'll hold an extra one tomorrow morning from 10:30 to 11:30. If you're planning on coming by this afternoon and you can't make any of my other office hours, send me an email to let me know and try and make something work out. I posted a new web work. It's going to be due on Monday. We'll go ahead and have the Standard 6 quiz on Friday, even if we don't quite finish Standard 6. We'll get through, I can still ask some stuff on, say, Type 1 improper integrals. And don't forget, you also have a homework due tonight and an exam next Wednesday. Just so you know, exam for next Wednesday will be over, we'll have questions on it from standards 1 through 7, including improper integrals and the next topic, which we'll do on Friday, which is how do you actually determine what integration method is the best one to use when it's unclear. Which technically won't be any new content, but just sort of talking about how can you strategize now that we have all these different integration tools, which ones are best to use in which circumstances. So, anybody have any questions or comments before we get started for today? Did you all know that my old car is like e to the x? You can try deriving it all you want, but you're not going to get anywhere. Okay, so last couple classes we've been focusing on Type 1 improper integrals, which are these sort of integrals where you basically have no upper or no lower bound on the area you're integrating over. So integrating from, say, some constant to infinity, or from some negative infinity to some constant. With the idea being you have this sort of shape with infinite perimeter that can still somehow have a finite area inside of it. And the way we would evaluate integral of f of x from a to infinity is you evaluate it from a to some variable r, and then take a limit as r goes to infinity. And what I would like to do today is talk about a different type of improper integral that has similar in the general idea of how you would go about solving it, but in practice requires a little bit of finesse. Specifically, we'll look at improper integrals that look like this. Let's do integral from 0 to 4 of 1 over 4 minus x. So I'm going to be on the page of the packet that says Type 2 at the top. So this may look like your typical definite integral, sort of thing we've been looking at for the past several standards. There's something insidious about this one. Something sneaky about this integral. Anybody notice, just looking at the function we're integrating and the bounds that we're integrating in between, what makes this a sneaky integral? Aiden?
When we plug in our upper bound 4, we get 1 over 0, so we will have an infinite upper bound, and then 4.
Yeah, if we actually try and graph out, for instance, what does this function look like over the region from, say, x less than 0. If we try and graph out something to tell us what does this function actually look like, if you were to plug in x equals 4 into our function, f of x equals 1 over square root of 4 minus x, f of 0 is fine. F of any number between 0 and 4 is fine. F of 4 is 1 over 0, undefined. And in fact, if we try and graph out what this function sort of looks like, we end up with a region that we're trying to find the area of that looks like this. With the idea being, it's sort of a lot like our graph of our type 1 improper integral, where the region we're integrating over is actually once again going to have an infinite perimeter because we have this vertical asymptote here at x equals 4. Our graph is getting really, really close to x equals 4, but it's not quite reaching it, and it's going to kind of go up forever. Meaning just like how this region kind of extends to the right forever in this type 1 graph, in this graph, our region is extending upwards forever. Yeah, Amy?
What does it mean that it's like dx over the square root?
Oh, it means that I got gung-ho about writing out dx, and I wrote it out twice for some reason, I don't know why. You can either write it as 1 over square root of 4 minus x dx, or you could just write it as dx over square root of 4 minus x. But one thing you should not do is writing dx over square root of 4 minus x dx, because that doesn't mean anything. Yeah, sorry about that. That's me just being, that's me being mean. So this is actually going to be a new type of region called a type 2 improper integral, which is very similar to a type 1 improper integral graphically. It's just that your region is going up or down forever instead of to the right forever. And the idea behind type 2 improper integral is at one of your bounds, the function, at one of your upper or lower bounds for your function, over the region that you're integrating over, the function's going to plus or minus infinity. So what we can say is if f of x is a function that's continuous on the interval from a to b, not including at the point b itself, but the limit as x approaches b from the left is plus or minus infinity, then integrating from a to b, your function, it's going to turn out, you could do a similar sort of trick to what we did over here, just integrate from a to r instead, and then take a limit as r approaches b from the left-hand side. So we're going to write it as limit as r approaches b this time from the left-hand side, integral from a to r, f of x dx. And similarly, we can say that if we have a function f of x is continuous everywhere except for the left endpoint of the interval, and the limit as x approaches a from the right-hand side is plus or minus infinity, then we can define integral from a to b of our function is just going to be the same as limit as r approaches a from the right-hand side, integral from r to b, I'm thinking Arby's. The idea being, instead of integrating from 0 all the way to 4, because our function is not even defined at 4, what we can do instead is we're going to integrate from, say, 0 in this case, to our variable r, and then just seeing, so that'll give us some expression in terms of r, and then seeing what happens as we push r to be closer and closer to 4. See what sort of limit we end up getting. So let's try that here. We want to evaluate integral from 0 to 4 dx over square root of 4 minus x dx. Just kidding. What we can do is, since we have a troublesome point at 4, we're going to use our dummy variable r in a very similar way to kind of what we did last couple classes with our type 1 improper integrals. And take a limit as r approaches 4 from the left-hand side, and then integrate from 0 to r 1 over square root of 4 minus x. And if it helps, you can put the dx out here or in the numerator. It means the same thing either way. All right. Yes, Phoebe.
Why does it have to be from the left-hand side?
Yeah, good question. Why can't we just say take a limit as r approaches 4 in total? Well, if we look at this graph, why would we want to take a limit as x approaches 4 from the left-hand side instead of just take a limit as x approaches 4? Or take a limit as x approaches 4 from the right-hand side even? Bethany?
Because if we took it from the right-hand side, then that would be a value greater than 4, and then that would make a negative in our square root.
Yeah. It depends. For you to answer your question, it sort of depends on the function, but really, we don't care about what happens to our function to the right of 4. As Bethany pointed out, this function isn't even defined for x greater than 4, because if x is greater than 4, we'd be taking square root of negative number, and it's no longer Monday's class. We're now no longer allowed to use imaginary numbers again. And so, since we only care about what the function is doing to the left of 4, when we're kind of looking for, hey, area from 0 to 4 like this, what I would say is we should only take a left-hand limit as x approaches 4. Or if we wanted to do or if we had something like square root of x minus 4, which is a very similar looking graph, but does this instead, something like that, then in that case we would only care about the area to the right of 4, just because that's the area we're integrating over. Does that make sense?
Yeah.
Cool. Yeah, good question. Glad you asked. Any other questions before we evaluate this integral? So, how do we evaluate this? How do we find, what technique do you think we could try to find a function whose derivative is 1 over square root of 4 minus x? I think put your hand down. I'm not calling that right yet. For now. Well, we have kind of a bunch of techniques at our disposal, so it's a little bit tricky to say. Does this look like an inverse? Does this look like an inverse trig derivative to anyone? Good. It doesn't look like one to me either. If this was 4 minus x squared, that would sort of look like something we would want to try maybe using an inverse sine function to as our antiderivative. But I don't think, since we only have 4 minus x in our denominator, not 4 minus x squared, I don't think there's going to be an inverse sine antiderivative. I know, you're all so disappointed, I'm sure. Kate?
So,
U sub? What would you suggest to sub for u then?
4 minus x.
Okay, so Kate has proposed we try a u sub on this to let u equals 4 minus x, which would make what? Du dx equal to negative 1, so du is negative dx. We don't have a negative dx, but we do have a positive dx, so that's the same as saying negative du is equal to dx. Okay, so limit as r approaches 4 from the left. What'll that give us? Integral from x equals 0 to x equals r, using the James method instead of the Rotem method because I don't see Rotem actually here today. What's that? The dx gets replaced with a negative du, and the divide by square root of 4 minus x becomes that over square root of u. Okay, yeah, that looks a little bit simpler to work with. How can we integrate negative 1 over square root of u du? And again, if the du in the numerator is confusing you, you can always just throw it out like this. James, how would you approach integrating this?
The reverse power rule.
Ooh, okay. Explain further.
So you can rewrite it as negative u to the negative 1/2.
Okay, give me just a second. You want to write this as negative u to the negative 1/2?
Yep.
Yep, because square root is take to 1/2 power. Dividing by square root of u means taking u to the negative 1/2 power. No, I'm feeling lazy. Okay, so James, what do we get when we use reverse power rule on negative u to the negative 1/2?
It's negative u to the 1/2 divided by 1/2.
Negative u to the positive 1/2 divided by positive 1/2? Yeah, I'm on board. Negative u to the positive 1/2, negative 1/2 plus 1 is positive 1/2, divided by positive 1/2. Which I think if we do a little bit of simplifying, will give us limit as r goes to 4 of what? Dividing by 1/2 is the same as multiplying by 2. So we'll have negative 2 square root of u from 0 to r, which we can then write as limit as r approaches 4 from the left-hand side of negative 2 square root of 4 minus x, evaluated from 0 to r. What do you know? Kate, I think your use of was a good one here, or was a useful one here. Neato Dorito. Any questions or comments thus far? So far, this has basically just been other than the writing limit as r approaches 4 out in front, this has been a standard 2 sort of integral. So now we need to plug in our bounds and subtract, which will give us limit as r approaches 4 from the left of negative 2 square root of 4 minus r minus negative 2 square root of 4 minus 0. Just plugging in our r, plugging in our 0 and subtracting, since just like we normally would with a indefinite integral. What does that limit come out to? As r gets closer and closer to 4 from the left-hand side, what can we say about negative 2 square root of 4 minus r? Joy, what do you think? What do you think about this limit? What's going to happen to square root of 4 minus r specifically as r gets closer and closer to 4?
It'll get smaller.
Yeah, 4 minus r will get closer and closer to 0 as r gets closer and closer to 4. And so negative 2 times square root of thing getting really, really close to 0 is going to get really, really close to
0.
yeah, this whole expression is going to go to 0. And so our final answer then is just going to be minus minus is going to be 2 square root of 4, which is 2 times 2, or 4. meaning this region here that we're integrating over from 0 to 4, even though, once again, it has this sort of infinite perimeter, it extends upwards forever, this region that we're integrating over, it can still come out to a finite area of 4 in the end. Phoebe, by the way, to address something you asked about earlier, if we were taking a limit as r approaches 4 from the right-hand side, or a two-sided limit, this limit right here would actually fail to exist, because if r is greater than 4, square root of 4 minus r would be undefined. So the fact here that we're only taking a left-hand limit as r approaches 4 actually ends up being pretty important for us, because otherwise we'd get a does not exist sort of error here. Okay, yeah, that's,
Just another question on the
keep them coming.
second to, or on the last step where we have, yes,
Here?
that, above that one. The reason we didn't write the limit with the second part is because there's no R in that section.
Yeah, technically we could throw in here a limit as r approaches 4 from the left-hand side. The thing about -2 square root of 4 minus 0 is it doesn't care what r is doing. So you're right, the fact that there's no r's that actually appear in this expression means I got a little bit lazy, didn't write that out. Which, whenever you're doing these, usually when you're doing these sort of improper integrals is going to happen. If you have, one of your endpoints is going to be a constant, one of them is going to be this r, which is where r is approaching one of your bounds or is going to infinity. And on the constant expression, you don't really need to write out the limit if it doesn't involve r at all. You could put it in if you wanted to, but it just wouldn't make any difference. So, type 2 improper integrals, I think, are similar conceptually to type 1 improper integrals, in that you sort of have these unbounded regions that you're integrating over. The difference is it's going to be the issue with type 2 is you have all this vertical going upwards or downwards stuff going on, whereas with the type 1 improper integral, it's horizontal instead, that the region extends off to infinity. Questions, comments, concerns? Alrighty, let's look at another one. I would like to look at the integral from -2 to 2 of 1 over x cubed. I'm giving you all this one because you all look a little bit flabbergasted, a little bit, I'm tired, whatever your name is, from that last example. So I thought I'd throw you a softball. Here's one where if you plug in our upper and lower bounds at 2 and -2, 1 over x cubed actually behaves nice. You're either going to get 1/8 or -1/8. So functions, nothing sneaky's going on here at our bounds like in the last example. So you might think we would do an integral from -2 to 2 of x to the -3. I'm going to purposely not call on you, Kate, for a minute. I'll call back on you for a second just because I want to have a dramatic moment here in just a second. And I have a feeling, and something tells me you're going to spoil that right now if I don't stop you. Which is, if we do reverse power rule on that, we'll get x to the -2 over -2, evaluated from -2 to 2. That's a lot of 2's. Which is the same as -1 over 2x squared from -2 to 2. X to the -2 is the same as 1 over x squared. Which is going to be -1 over 8 minus -1 over 8, which is going to be -1/8 plus 1/8 equals 0. Sort of, standard fundamental theorem of calculus, Calc 1 standard 17 sort of problem. Unless, Kate, you have something you want to say about this integral.
I was just gonna say, you can't have 0 in there. So,
X can't equal 0, sure. What's why is that a problem?
because it creates like a hole in the graph, so you couldn't just do the entire interval from -2 to 2. You'd have to split it into 2 intervals.
Holy moly! Kate is right. What we just did here is a pack of lies. For a very sneaky reason. If we wanted to graph out 1 over x cubed from -2 to +2, here's what the graph would end up looking like. We have this big problem point in the middle at x equals 0. Because Kate's absolutely right. The function f of x equals 1 over x cubed is undefined smack dab in the middle of our interval from -2 to 2 at x equals 0. And technically, we can't use the fundamental theorem of calculus to evaluate this definite integral unless the function is continuous everywhere inside of the region we're integrating over. Yeah, Gabe?
So, I'm saying it seems like we're still gonna get 0 for an answer, just because we're gonna take, and it's just gonna be a region below the x-axis and then an equal region right above it at the x-axis, so.
Yeah, so it seems to me like we have this area that could potentially be infinite underneath the x-axis, and then this positive area, which could also potentially be infinite, but feels like it should be the same as this area above it.
But it's x to the third, so we already know that it converges, right?
Do we?
Oh, wait, no, because they haven't done type 2 integrals. Okay, alright.
I was going to say, if this was a type 1 improper integral, then yes, we would know that from Monday's class, but we haven't talked about how to handle a p integral for type 2 improper integrals yet. So the problem with this approach is we technically can't use the fundamental theorem of calculus since the function f of x isn't continuous over the whole region. I'm sure all of you spend every night looking back over your notes at Calc 1 and remembering what were the necessary conditions in order for the fundamental theorem of calculus to actually apply. But for the 1 or 2 of you who are slacking off in your duties and who aren't looking at that every night, part of what you need in order to use fundamental theorem of calculus is your function has to be continuous over the whole region. So, Gabe, it sounds to me like your intuition is telling you you think this area should come out to 0 regardless.
Yeah.
This is noise. I think that's just building noise. But I don't think we can use just this plain old vanilla fundamental theorem of calculus just like what we did here in order to determine that for sure. So, Kate, it sounded like you had an idea for how to get around this conundrum. What did you suggest?
Splitting up the intervals.
Okay, split it up into 2 separate integrals. Yeah, so what we can do instead is we can split integral up into two different type 2 improper integrals. So let's try doing that and seeing what happens. So what we're going to do for this sneaky integral here is I'm going to split it up into, take the area from -2 to 0 and add that to the area going from 0 to 2. Because from 0 to 2, this is hunky-dory, or at least it's just a standard type 2 improper integral, similar to the one we just did with the square root of 4 minus x. From -2 to 0, we have a similar sort of improper, type 2 improper integral going on. So by kind of splitting up our integral with a problem point in the middle into two separate regions, each kind of, this one bounded above by the scary point, this one bounded below by the scary point, the scary value of x equals 0, I think we can make this work out a little bit nicer. So, question. How can we write out a limit involving r, similar to what we did in the last problem for this first type 2 improper integral? Or is that a hand?
Sure. So
It's a hand now. Nora, I volunteer you.
it's the limit as r approaches 0 from the negative side.
Limit as r approaches 0 from
The negative side,
the left. Okay.
from -2 to r.
Yeah. The problem point is at 0, so we can just say take a limit as r approaches 0 from the left-hand side, and area from -2 to r, and then just let r move closer and closer to 0 here. 1 over x cubed dx. And then, Caleb, how could we do something similar for the right-hand integral?
Would it be lim as r approaches 0 from the right of 0 to r of 1 over x cubed dx?
Like that? I like it. Yeah, that's exactly it. Same sort of integral here. And instead of integrating from scary point 0 to 2, let's just integrate from r to 2, and then take a limit as r moves closer and closer to 0, this time from the right-hand side. Because in this case, 0 is at the left-hand endpoint of our integral.
The building is alive.
Hush! Dang it, sometimes that works. Alright. Ignoring the ghosts in the belfry of... Hey, Moss. Hey, Dr. Martin, please get us a new building. Yes, Phoebe.
Is it supposed to be like r and 0 for the integral? Like, how does that make sense?
How does that work? You're right, it doesn't. I was getting so wrapped up in like scary noises that I put down the wrong bounds. Right, Nora, is that what you were asking about? Okay. Yeah, good catch again. These sort of little mistakes are very easy to make if you're not paying close attention to what you're doing. What you made me do. So from here, I think we can integrate the same way that we've kind of been looking at with our whole just find the antiderivative of 1 over x cubed, where we kind of already did that over here. The antiderivative of 1 over x cubed came out to -1 over 2x squared. So we'll get a limit as r approaches 0 from the left of -1 over 2x squared from -2 to r, this time I'll try and be careful, plus the limit as r goes to 0 from the right-hand side, -1 over 2x squared, evaluated from r to +2. So let's evaluate these two limits. So here I skipped a couple of steps going from 1 over x cubed to -1 over 2x squared, but that was just using a reverse power rule like what we did in the stuff I crossed out. The problem here wasn't in using the reverse power rule, the problem was in our dealing with our bounds. So if we do that, we'll get what? A limit as r approaches 0 from the left-hand side of -1 over 2r squared minus limit minus -1 over 2 times 2 squared. And yes, Phoebe, if you wanted to, you could include another limit as r goes to 0 from the left in there. It wouldn't make any difference if we did, but you could if you wanted to. Plus, we'll have -1 over 2 times 2 squared. Frankly, this is -2 squared, but -2 squared and 2 squared are the same. Minus limit as r goes to 0 from the right-hand side of -1 over 2 r squared. Everyone on board so far? Alright, James. As r approaches 0 from the left-hand side, what's going to happen to -1 over 2r squared?
It's going to get really, 0 from the left.
I'll give you a hint.
Also-
Since you're squaring r, whether you're taking r going to 0 from the left or the right doesn't actually matter here.
But so, since we're taking a limit, does it matter that it goes undefined, or can we take it like going up infinitely in some direction?
Well, you're right. It's undefined. We can't plug in r equals 0.
Yeah.
But what is the limit doing? Is this going to a finite number? Is it going to infinity? Is it going to negative infinity?
It's going to negative infinity, I believe.
Yeah, we have -1 over really, really, really big positive number. I think that limit's going to negative infinity. As is this one, for the same basic reason. Since we're squaring r, as r approaches 0 from the left or right, r squared is going to be positive regardless. So we'll have -1 over not super big positive number, super small positive number, which is going to go to negative infinity. Jonah?
So is it only going to negative infinity because of the negative sign?
Yeah. If this was a positive here, if this was a plus, then this would go to positive infinity instead.
Okay.
So, what can we say about this expression? Gabe?
Yeah, so just to clear up, we're saying it goes to negative infinity because as r gets smaller and smaller, the fraction increases.
Yeah.
Okay.
Yeah, so if we take a look at this integral, or this, not this integral, this limit here, what we would end up getting is something like -1 over a very small positive number. And in general, if you take 1 over something really, really small, like 1 over 0.001, what sort of number are you going to get from that? 1 over 0.001 would be 1,000. So the closer that r gets to 0, the smaller your denominator gets, and if your denominator's getting really, really small and your numerator's not changing, the whole fraction as a whole is blowing up. It's getting super, super big. And how do we know if it's going to positive infinity or negative infinity? Well, numerator's always negative. Denominator's always positive as r gets close to 0 from the left, or from the right for that matter. So we would say it gets really big in magnitude and it's always negative, so the limit goes to negative infinity. There's a hand back here. Aiden, can you- I'm good.
Yeah, I was wondering if, since it's coming from the left, it was going to go to negative infinity because we're pointing smaller negative numbers, but it doesn't matter because it's squared.
Yeah. The fact that we're squaring r here means the direction r is approaching 0 from doesn't matter. If this was like r cubed instead of r squared, then it would matter. And in this case, I would actually say the limit would come out to -1 over very small negative number, which would go to positive infinity, to positive infinity, because the negatives in the top and bottom would cancel out. But the fact here that we have a square means no matter which way r is approaching 0 from, denominator is always positive. -1 over positive is always going to go to something negative. Well, we have two different limits in our expression going to negative infinity. So what can we do about this? So, I think we've reached a decision. There's two different things that we could try to do here. All right, Bethany, I'll take you off probation for the moment. What would you suggest?
Well, we can combine the two negative infinities. It's like negative infinity minus infinity is just negative infinity.
Just say this limit combines with that one to cancel out, so to speak. Because technically this negative infinity is going to get it added to a positive, or we're going to have negative infinity sort of plus infinity here, because this negative infinity is getting subtracted off. So they would cancel out, you think? No?
It's impossible. That's one of our forms that it's undefined. It doesn't work.
It doesn't work. James, what do you suggest?
Just stop and say it's divergent.
Just stop and say that the whole expression is divergent? So this is tricky. Actually, Gabe, before I say anything, I want to ask you, what do you propose we do? Because you're the one who wanted to just say, oh, they cancel out earlier.
Yeah,
So what we've shown at this point is this area is actually infinite on the left, and this area at this point on the right is now infinite.
Yeah.
Do they cancel each other out?
I mean, they should be equal wherever they are.
They're equal infinities?
And there's equal area above and below the x-axis.
So this is sort of an interesting idea, and one that we're going to be coming back to more later in the semester. We sort of have all of this, we have infinite area down here. We have infinite area up here. Usually when we say infinite area, we freak out and say, oh my gosh, it's divergent. And that's tone of voice for some reason. But we also usually would say something like, oh, if you have the same amount of negative areas, you do positive area, and these areas certainly look the same. This function is nice and symmetric around the origin here. If you took this region and you rotated it 180 degrees, it would line up perfectly with that region. Normally in that case, we would say, oh, the positive and negative area cancel each other out, leaving us with a total area of 0. So I think it would personally, I think it would make sense, James, to take your approach and to say, it's divergent. Or Gabe, taking your approach and saying that they cancel each other out and give us a total area of 0. I think that there's a solid argument to be made for both of what you suggested. There is a convention for this that mathematicians have kind of arbitrarily decided on. And what we are going to be doing is taking the James approach and saying, oh my gosh, infinite limits. this integral diverges. But that's sort of like but there is a choice that's being made here. How do you want to deal with these infinite areas that seem to sort of be canceling each other out in a sense? Like if this area had come out to -2 and this area had come out to +2, for instance, we would have just said, oh, they cancel each other out, give us 0 without a second thought. But the fact that we have these two infinite areas, anytime you have this sort of infinite area showing up as part of it, we're going to immediately stop and say, hey, this is a divergent integral. But Gabe, I think if we had done your way, I think would totally make sense as well. Yeah, 8.
Sort of slightly off topic, but will we ever have to worry about indeterminates?
Indeterminates, technically this is sort of an indeterminate right here. So I would say yes. Are you thinking like indeterminates in the form of L'Hopital's rule type stuff?
Yeah, like 0 times infinities, negative.
Eventually, yes. We're going to see a lot of those once we start talking about series. So not quite yet, but in a few standards from now. So this is making a choice. We're going to say that the integral diverges. Where if you remember from the front page, we said a convergent integral is sort of like an improper integral where that comes out to a finite area. A divergent integral is one of these integrals that comes out to an infinite area. Or when we plug in the limits, we get either a limit of infinity or does not exist. Technically, what we've shown is that this goes to -infinity, this goes to +infinity, and we've taken our nice, benign-looking 1/x³ integral. I lied when it said earlier that this is a nice, simple Calc 1 integral. We've taken this nice, simple one and broken it up into 2 divergent improper integrals. And the way that we're choosing to handle this is to just say the overall expression diverges because the 2 individual pieces diverge. But I think there is a reasonable argument to be made for saying that they cancel each other out as well. Here's a theme that we're going to be looking at for going forward in the semester. Infinity is weird. And so saying do 2 infinities cancel each other out, it's hard to say. In my real analysis class, actually, we've been talking a lot about infinity. We just proved the other day that there are infinitely many sizes of infinity. What the heck does that mean? There's infinitely many sizes of infinity. Take more math to find out. Any questions or further questions or comments about what we did here? I know we kind of spent a long time going over this one example, but it's a really weird one, and one that I think is definitely well worth spending some good time discussing. Cool. So, I'm just going to tell you all right now, this point, where we're at right now, is the cutoff point for Friday's quiz. Standard 6 still is going, and we're going to keep talking about Standard 6 for the next 15 minutes and a little bit into Friday's class, I think. But this is the cutoff point for what you need to know for the quiz, kind of how to handle these type 1 and type 2 improper integrals. And no, I'm not going to ask on Friday, on the quiz Friday, anything about like what we did in the I to the I proof. That was sort of what I would consider to be a cool, fun aside that kind of uses this idea of improper integrals to do some weird imaginary number math. But it's not something I'm going to ever quiz or test you over. However, stuff we're about to do could show up on the Standard 6 question on the exam or on a retest. Just not Friday's quiz. Alright, so I want to look next. An integral from 3 to infinity, skipping ahead a couple pages for just a second in the packet, 1 over square root of x minus 1 dx. Which sort of looks something like, looks something sort of like this, actually. So this is a type 1 improper integral again, because the problem is not at, we don't have a finite bound where the function is blowing up, going to positive or negative infinity. Instead, we just have an upper bound of infinity that we're looking at. My question is this going to come out to a finite area or to an infinite area? A little bit hard to say. The function's getting smaller and smaller, so it could be a finite area, but since we're integrating over an infinite region, we've seen examples at this point of type 1 improper integrals of shapes like this, where the area came out to something finite, but we've also seen examples at this point of regions like this where the function would come out to something infinite as well. So let me ask this question. How about this integral? Is that integral going to come out to a finite value or to an infinite value? Okay.
We said that it diverges.
Well, we can write this as integral from 3 to infinity of 1 over x to the 1/2 power. And when did we say that that diverges?
I think we said that the exponent has to be greater than 1 for it to converge.
Yeah, that was our sort of p integral test from the first half of Monday's class. We said that if we ever have an integral of the form, say, like 1 to infinity or 3 to infinity, the lower bound here doesn't particularly matter, 1 over square root of x, or 1 over x to the p, we said, will converge if p is greater than 1, and it's going to diverge if p is less than or equal to 1. That's something that we proved in Monday's class on the, third page of the packet, I think. We called this a p integral. So, Gabe, you're saying that, hey, we have a p integral here where the p is 1/2, which is less than 1, so the integral diverges? Yeah, I would agree. This integral is going to diverge as a p integral with p equal to 1/2, which gives us a value that's strictly less than 1. Let's do one more graph, see if we can find out something that's going on here. I want to make a comparison. Square root of x and square root of x minus 1. Taylor, which of these two expressions is going to be bigger? Square root of x or square root of x minus 1? Yeah, because if you subtract 1 from something, you're making it smaller, right? All right. Joanna, square root of x is bigger than square root of x minus 1. What's going to be bigger, 1 over square root of x or 1 over square root of x minus 1.
1/.
This one's going to be bigger? Why is that?
Because you're not subtracting anything from the denominations.
Ah, so you're saying like the denominator is bigger on the left-hand side, so the fraction's going to be bigger? In the same vein as you would say something like, oh, 1/2 is less than 1/3 because this one has a bigger denominator? Oh, you're just kidding, it's the opposite? Oh, someone else wants to weigh in. It's actually a less than. I know. Ooh, that's so exciting. The idea is when you take a when you have A, if A is less than B, you're going to have that 1/A is actually greater than 1/B. Sort of a rule of fractions. It's like saying 2 is less than 3, which actually makes 1/2 greater than 1/3. So when you take reciprocals, you're going to flip around. So let's take a look at these two functions from 3 to infinity. So from 3 to infinity, 1/square root of x is going to look something like this. As we just finished discussing, 1/square root of x is always less than 1/square root of x minus 1. So g of x here equals 1/square root of x minus 1 is going to include a bigger area than f of x would, I would say. So here's the question. We just showed, or according to Gabe, I think, the integral from 3 to infinity of 1/square root of x, this area here is an infinite area. Because that integral, we said, goes to infinity. It's a divergent integral. Sarah, what would you expect the area under 1/square root of x minus 1, this g of x area, to be? Would you expect the area under g of x to be a finite area or an infinite area?
Probably infinite.
What? Hush! Why infinite?
Would it be infinite?
Why do you say infinite?
Because it's similar area, but only up higher.
Yeah, it's basically the g of x area is going to include all the same area that the f of x area does, and then some. The fact that g of x is greater than f of x means that g of x is going to get all of that f of x infinite area and then some more. Infinity plus some. And so, if we want to then go back to our initial integral from 3 to infinity of 1/square root of x minus 1, Mary, is this going to be a convergent integral or a divergent integral then, according to what Sarah said? Why convergent? You don't know? I need to stop asking questions to the quieter students in the class while the building's wailing at me. I think it's a little hard to hear. You sound uncertain. Would you like to phone a friend? Okay, pick a friend. Kate, I picked you.
Okay. What was the question one more time?
Would you expect this integral right here to be convergent or divergent, according to what Sarah was saying?
Divergent.
Yeah, it's actually going to be a divergent integral because, as Sarah pointed out, the area under this function from 3 to infinity we would expect to be infinite because the smaller function has an infinite area from 3 to infinity, so we would expect this bigger integral to also have an infinite area. So we can say that this integral is going to be greater than the integral from 3 to infinity of 1 over plain old square root of x dx. And we know that that integral diverges In this case, it goes to positive infinity. Thus, we can say that the integral from 3 to infinity of the original integral, the one we cared about, must diverge as well. By comparing it to this other integral. We have more area than this infinite area integral. Therefore, the area that's bigger than the infinite area must also be an infinite area. And that is going to lead us to what I would call, stop teasing. That is going to lead us to our big theorem for this standard, kind of the last thing, which is called the comparison test. Where the comparison test gives us a way of knowing when an improper integral is going to converge or diverge by comparing it to some other integral. So if you write that out, you can say for a comparison test that if f of x is greater than or equal to g of x is greater than or equal to 0 on the interval from a to infinity, meaning if we have a point here, let's say a, if this is our f of x, and then say this is our g of x right here, and we can make a comparison about the areas by saying if the integral from a to infinity of f of x converges, the f of x area converges and the g of x area also converges. Oh, okay, yeah, I was gonna say, that doesn't look right, but that's because I had my pictures backwards. F of x is greater than g of x. If we know that the larger area turns out to be convergent, if the larger expression comes out to a finite area, then the integral from a to infinity of g of x must also converge. And similarly, we can say if the integral from a to infinity of the smaller area diverges, then the integral from a to infinity of the larger area must also diverge. With the key idea being, in the second case, the one we just saw an example of, if the g of x area is infinite already, then adding more to an infinite area will still give you an infinite area. And if the f of x integral converges, meaning if the bigger area is finite, then the area that's smaller than this big infinite area, or than this finite area must also be a finite area. Have a good day, everybody. Like I said, we'll talk a little bit more about the comparison test and how to use it on Friday. I won't ask you about the comparison test for the Standard 6 quiz, but it could appear on retests and on the exam. But we'll do some more examples and talk more about this at the start of Friday's class before we move on to Standard 7. Meantime, hope you all have a good one. See y'all on Friday. Don't forget my afternoon office hours today is being moved to tomorrow morning.